Good afternoon. This is our session on second session on technology. This is a presentation by Sami Kanderian, who has taken this development of WikiModel as a project of love and care, and is in the middle of figuring out where we go with this. But the most important thing is to inform people of its very existence. And when you get on and play with it, you will be pleasantly surprised. That's an understatement. So he's going to talk to us about WikiModel and how to use it. And then after this, we can adjourn and have additional discussions in the next period. So Sami, I'll turn it over to you.
Thank you very much, Brian. I appreciate the opportunity to present this again. This is my second Simiode where I'm presenting. Hello?
Yes, I'm sorry. You're okay.
Okay. So yeah, I'm happy to present on this application, and this is an application that anybody can use. You just go to wikimodel.com. And you can register for an account, and it's free for all to use. So I'm hoping that you would try it out. And there's a couple. If you need instructions on how to use it, you can hit. There's an About button when you go to the web page, and we'll go to the web page when I'll show a quick demo of how to use it for a particular example. So I'm not in academia, but I've spent a lot of time. I'm in the industry, and my background is in biomedical engineering, and I've used a lot of differential equation modeling for modeling insulin and glucose pharmacokinetics and pharmacodynamics, in particular in type 1 diabetes to optimize glucose control, and that's sort of where my interest in mathematical modeling sort of came to be. And sort of when you're creating these models, you have to be a programmer, and you have to put a lot of time into coding. And when you're coding ODEs, or ordinary differential equations, there's additional coding that has to do with integrating your equations. And then if you're fitting your model to experimental data, which is really important in real world scenarios. Otherwise, your model is worthless if it doesn't replicate the real world. I think somebody's microphone is on. There we go. So yeah, I created WikiModel to sort of remove a lot of the hurdles, especially in education, if you're like a freshman and you don't have any experience with coding. So WikiModel is a web-based software tool for simulating and fitting models. As I said, it requires no programming, and you just basically enter the equations as they appear in the textbook. And it also is an application that's web-based. It doesn't require any download or installation. And you can simulate any number of differential and or closed form equations, and it plots the results on the screen. And it also allows you to handle discrete inputs or disturbances to your models at different times. And I think what's really neat about this, and what I really needed to do in my work, was to fit the model to experimental data, because what I was doing was simulating a virtual patient. So I had experimental data from real patients with type 1 diabetes, and I created this model that replicated their data. And then what I could do is change my control strategy, or their insulin delivery strategy, and see what would have happened if they had done things differently. And then we run an additional clinical trial to validate sort of the predictions. And what's also really cool is once you create a model, you could share it. You could share it with a group of people. You can make it public to anybody in general, or you could keep it private if you're sort of playing around and you don't want other people to see what you have. So I wanted to do a quick, to demonstrate WikiModel with this example. So what I did is I actually ran this experiment at my house where I created this apparatus with a solenoid that sort of launches this ball with a switch, and then I set up my my smartphone camera to take this video. And so what I'll do is I'll play the video, and the video will play at 1 frame a second, but in real time it's 30 frames a second. So I'm going to go ahead and play it. So you could see that I wrote some software to track the position of this marble over time. And again, I slowed down the video, but my point here is I've collected the position over time, the X and Y position of this marble. And the problem here is, well, can we, based on the data that we collect, what is the initial speed, the initial angle, and the drag coefficient of the marble? So let's use the WikiModel tool to find out. So first thing we have to do is derive our model equations. So in this case, we're concerned with both the horizontal and vertical components. I've got the force equations, and from the force equations, you can derive the acceleration in the X and the Y position. Now, in this model, we're also assuming that drag does exist and that the drag is proportional to the speed squared at any point in time. And so we need these other equations that consider the drag and the changing speed and angle over time. And so when you use all these equations, you translate it into this differential equation set where, you know, the derivative of position is velocity in each direction, and the derivative of velocity is acceleration. And, you know, as I mentioned, we need to monitor the speed at all time and the angle at all time. So this is our complete set of equations. Now I have G, which is the gravitational constant. I have that as an equation and not a parameter, and I'm going to explain why. So what I call parameters, or what WikiModel considers parameters when you type them in, is you can actually identify the parameters, or you can fit them to your data. I'm not trying to fit the gravitational constant because I know we're on planet Earth, and I know it's 9.8 meters per second squared. So now what's kind of interesting about this model is, because of this velocity squared component, because the drag is proportional to the square of the speed, you can't isolate the individual components. You have to consider both of them. And furthermore, there's no analytical solution for the X and Y trajectories. Of course, we know that when there's no drag at all, we don't need to, we don't need to express, to integrate differential equations. We can just use the analytical solutions, right? But for this problem, since we're considering drag and there's a square term here, we have to use, we have to use an ODE-based model. So what I'm going to do now is I'm going to bring up my application. So let me see if I can do that here. So if I go, here. So here's my web page. So I'm logged in. So anybody can create an account and log in. What you see on the left-hand side is a whole bunch of models that I created in different scientific disciplines that you can load. So you don't actually have to start from scratch, but you can start from scratch if you wanted to. So here are all the model equations. And as I said, you type them in as they appear. So here, this is the exact same equation set I had in my presentation. Now, in this example is kind of unique because what we're fitting is we're fitting both the X and Y position. And so what I have is a minimization function. So I had to create this additional equation that says I'm minimizing my distance to the data at any point in time. Usually you're just fitting one parameter, and that parameter is a variable that you already have in your equation set. But since this is kind of unique, where the minimization function is a function of two state variables, we have to create this equation. And what we're saying is we want to fit this minimization function to a bunch of zeros because we're trying to minimize that error. sum squared error. Now, you do have to put in the data. So here's my data where I said I had to, I collected the data from my image processing where at every time where the ball was in flight, I located the X and Y position and I typed them in here. So now if we go to the model, you could see that here are my parameters. And for any parameters that you type in, if you hit simulate, it actually, hey, it doesn't fit your data. It simulates it for that particular set of parameters that you entered. So here I'm plotting X versus time, Y versus time, and this is the actual trajectory, which is Y versus X, which is what we saw in the video, right? You can also plot other things, like here I'm plotting speed versus time, and you can see that my speed drops to 0 and then increases again. It drops to 0, as we know, at the very height of the trajectory. And what I have also plotted here is my data. So you could see that my simulation doesn't go through my data, right? It's sort of underestimating things. But what's cool is, I can change the numbers, right? So I can say, well, let me increase my velocity. Let's make it 1.2, and I can increase my drag. I can make this 0.4, and I can re-simulate things and see how that changes my output. Now you can see it changes my output, but what's again really cool about this is now I could say, well, I really don't know what my initial velocity and my initial angle and my drag coefficient are, but let me see if I can fit it. So I can hit this fit button. And now you could see when I hit the fit button, it's giving me the results for my initial velocity, my initial angle, and my drag coefficient K. And here's the answer. And you could see that using the fit values, my simulated model goes through the data really nicely, right? I'm showing you the X position versus time, the Y position versus time, and it goes through the data points really nicely. So that's what's really cool about I think about this is not only does it simulate models, you can put any number of equations, you can fit the model to the data, and so you can run experiments with your students where you collect experimental data, and you could say, well, let's try to see if our model works, right? So here we could clearly see that this model describes the data well. So now I'm going to go back to my slides really quick, and I want to sort of wrap this model up and leave some room for questions. One question you could say is, well, was the drag coefficient really necessary, right? So let me go back to here. So I can remove, the fastest way for me to remove the drag coefficient is to remove this variable K, right? So I can delete that. And I'll add it as a constant. Remember, if I'm adding it as a constant, I have to add it as an equation and not a parameter. So what I'm going to do is I'm going to add this, and I'm going to say K is equal to 0, right? So K equal to 0 means that there's no friction in this model any longer. So now when I do that, I can fit the model again. So let me simulate it first, and I can fit the model again. I'll hit fit. And when I fit the model without considering the drag in the model, you could see that this fit is still really good, right? And so what this is saying is you can, if I go back to my presentation, you could do statistics, right? Using an F test or a K-key decision criteria to figure out, based on the sum squared errors and the number of parameters, what the F test here is showing is that since this p-value, comparing the two different models where you have the number of parameters and the sum squared error, when you consider drag and when you don't consider drag, what the result is telling us is that really that we didn't really need to consider drag in this experiment. That's not to say that drag doesn't exist. It just means in the operating range of velocities that we're looking at, we didn't need to consider drag. If I had let the marble kind of reach terminal velocity, it would have been significant. So these are some things that you could play with. And, this is just one example. I was actually served as a judge for this year's SCUDEM competition, and I was a judge for the, dog can't catch. And so I thought this was a neat one to share an example of. I do have so many, as I mentioned, I do have so many built-in examples, and this is just a select few. I tend to use a lot of examples in the biomedical sciences space, since that's my background. So I have, this virtual patient in type 1 diabetes. I have a lot of pharmacokinetic and pharmacodynamic examples. I have a COVID model that I simulated that replicates a Nature journal, an electrocardiogram, and there's so many models that you can look at before you even create your own, just to get you started. And really, that's all I had to share. And I'm hoping if there any questions, I'd be willing to happy to hear them.
Yeah, just speak up if you have a question or a comment.
Yeah. Oh, sorry.
Christoph?
Yeah, this is fantastic. I think I have already gone to the webpage actually while you were speaking and try it out. I think this is really fantastic, especially the ability to match to data with your parameters. And the last thing you said, that the drag is actually not necessary. I wouldn't have known this. If you had asked me half an hour ago, I wouldn't have known whether or not it's really needed for this experiment. But one question I have is, has it been used in classes?
No, that's why I'm here. I'm hoping you will.
Okay. Thank you.
Tom Mussman?
Yeah, so at least my limited experience teaching differential equations, what always gets students with technology is the syntax, right? So you kind of, you seem to have this elegant way to kind of, you put, d theta dt or something like that, or I guess, have you done any, like, how should I call it, robustness to student ingenuity and their ways of messing up syntax?
Yeah, that's a good question. That's a good question. So this, you can, if you type in nonsense, if you type in equations with errors in them that can't be interpreted, for example, your simulated output will just look like a bunch of zeros. In other words, it won't give you an output. So I do have to add feedback that specifies, hey, you made an error and the error is in this equation. Please revise that one equation. So you can, if you type in the wrong things, it won't give you an output. And you kind of will know, because it'll sort of spin and sort of return with nothing, with no result. And actually, it works, the back end works on an API, which actually is visible in one of the tabs, and you can see that it's returning nothing. But to answer your question, hopefully this will, this obviously eliminates the need for coding. So I'm hoping that, the errors in implementing simulations will significantly go down. But of course, it can still, not behave if there's incorrect inputs to the equations.
Yeah.
Oh, sorry. So we use Mathematica, and it has all these wonderful output codes that people like, me who have been coding for a little bit, they're like, oh yeah, I know what that means.
Yeah.
But you hand it to a student, well, one, it costs a fair license fee. But you also hand it to a student, and the error code comes back, and the student thinks the error is written in French. And
Yeah.
They're stuck, and so kind of this
Yeah.
At least at the introductory level, kind of trying to get over that hurdle of student ingenuity is a challenge.
Yeah, no, I definitely think, it would be really cool if there was an error. It usually is in the syntax of the equation, or maybe they type something wrong, like maybe instead of typing SIN for sign, they typed in SINE, which doesn't work, and things. So, I will say that I do have some instructions. So if I Am I still sharing my screen?
Yes, you are. Go ahead.
Okay, so I do have an instruction page, right? So here it tells you how to log in, how to load existing models, sort of what sort of mathematical functions that you can use, and you can even upload your data, so you don't have to type them all in. I don't have cut and paste available to, you could cut and paste a block of data points. I'm working on implementing that, but you can upload a text file if you've collected your data and you have it in a spreadsheet and save it as a tab delimited text file. You can upload it. Like here, I've got certain equations and your data, and you can upload it. And here's a list of mathematical functions. You can even do conditional statements. You can even do conditional statements with ands or ors. And I noticed that I didn't specify that you could put ands or ors, so I need to update the instructions. But yeah, I hope that you give it a go. To also go back to Christoph's question, I don't have students using it, but I did have a professor who's at Georgetown University who somehow found me. Actually, I think he found me because of the Simiode video that I made last year. And one of the examples I gave was this 3-compartment bolus response for drug delivery. And he sort of reached out to me, and he's a professor of surgery and pediatrics, and he had used my model and made some modifications to suit his needs, and we had some communication. This is just a month ago, and so I sort of have his testimonial sort of as a plug for folks to encourage folks to use it. And so I haven't had a whole classroom use it. I've just had sort of 1 or 2 users that have sort of come across my site. And so I'm really trying to network to, get people in academia especially to use it. So I hope it's something that'd be useful for you.
Yeah, on Tom's question about, the syntax and the feedback and everything. So I'm on the opposite spectrum from the students at age 80, and I am finding, a set of, with all software, some issues. I found the best way is to look at what Sami is offering as worked examples. I mean, most of us learned LaTeX by looking at other people's files, and so we also go online now, of course, and look at how do you do this and that. But with Sami, I think the instruction sets that he's given and the examples are the richest thing. And when you do something syntactically wrong, the fact that it doesn't do anything tells you there's something wrong, at least. It may not tell you immediately, but you can see that. And the other thing is the full cycle modeling that he's offering here of parameter estimation with ease. You saw how easy it was to fit the differential equation model and finding its optimal parameters. Now, he was dealing with a physical situation, so it better be really good unless your data is bad. But if you're dealing in social science, it's not going to be perfect. Even in physiology, you may not get the data because of fuzziness. But I've used it. I'm not teaching any longer. And I agree with the surgeon who said, I wish I had this when I was going through certain things. So I want to encourage you. It's free. You just go online. You just do it. You play with it. And Sami would love to hear from you about questions or, suggestions, or I used it and this is what my students said about it. We will probably have a workshop in the spring devoted to this, as well as several other softwares. And at that time, we'll send out an announcement saying, this is another maybe 2 hours, and Sami and I are discussing maybe some Saturday afternoon. So you can get some more interactions with it. But are there any other questions, comments? We could have an altar call, to come on down and say a praise, and I'll use, but I'm not going to do that. Jenny, were you having a question? No, somebody was. Okay.
Can I ask? I'm sorry, I don't have this emoji with raised hand, so I am raising my real hand.
Okay.
I wonder, you are optimizing differential equation coefficients, right? Not the solution. in this optimization problem that you showed on one of the slides, so you are optimizing towards the coefficients of the differential equation and then solving them.
Right. So you know, the differential equations are integrated according to the equations themselves and the parameters that you specify here. But when you hit fit, what it is it figures out what's the best set of parameters that minimizes the sum squared error between your experimental data to the state variable that you're fitting to.
Mhm.
Does that answer your question?
So optimization is towards the solution curve.
To the
Okay.
yes
Yeah.
to yes.
So in that line, are the solution strategies you're doing numerical?
Yes.
Okay, so your estimating of the parameters is doing a lot of work for us because it's yeah, it's
Yes.
doing some descent or gradient or some
Yes.
sophisticated approach.
Yes, it's
And
doing
it's-
nonlinear least squares via an Elder-Mead steepest descent. algorithm.
All of that in the background and roughly instantaneous feedback, right?
Correct.
And no coding.
Correct.
Yeah.
And it also lines up your, you know, your data. Like here, my data is not, you know, my equation goes from, you know, 0 to 0.3 seconds at every 0.01. So a couple of things about that is it does use Runge-Kutta to integrate the equation. So it's not, it's still, you know, calculating the integrated differential equations at times in between the, you know, the what you specified, but also the data does not have to have the same timestamps as your model simulation, and it sort of figures all that out and pairs the correct time, the data to the correct time of the simulation. So all that it does without coding. But if you were to, you know, code it yourself, you would have to line up the data points, and if you had inputs, you would have to start and stop the differential equations and change your initial condition every time you have a new disturbance to your model, whereas this sort of handles it seamlessly.
Okay, we're going to curtail this session and suggest that if you want to continue discussions, you go to the sessions and you go down at the next time period to the discussion times on WikiModel. We're also having a parallel, and Bertram is going to moderate the discussion, and then we're having a parallel session on arts and humanities. Frank was talking about that yesterday, and we'll see if there's any interest in mathematics and arts and humanities. So let's thank Sami once again, and we will move on. Thank you.
Thank you.